So we know if we have this positive charge, what's going to happen if we throw in another positive charge right next to it? Well, we know they're going to repel. We know this positive charge is going to move. It's going to feel a force and it's going to move away. It's going to repel. So why will this happen? What's going on? We know they're not physically touching. So what's going on? Why does this charge feel a force? Well, let's remember this original charge. So all charges create invisible electric fields. So you can't see them, but this charge creates these electric fields. And what's important is the closer you are to the charge, the stronger the electric field. The farther away you get, the weaker the electric field. So we know this charge creates these invisible electric fields. And the key point of this video is whenever you have an electric field, for example, right here we know we have an electric field. If you throw in a charge in an electric field, that charge will feel a force. So that's the key point of this video. Whenever you have an electric field, if you throw in a charge, that charge will feel a force. And just the convention humankind has used are these electric fields point in the direction a positive charge would go. Because we know if we threw in a positive charge, we know we have a charge in an electric field, so we know the charge is going to feel a force. Which direction is it going to go? It's going to go in this direction, and that's why I drew the electric field in this with this arrow pointing in that direction. And again, that's just the convention. For example, what if we had a negative charge particle? What would happen if we threw in a positive charge? Well, we know this charge created these invisible electric fields. So whenever we throw in a charge in an electric field, it feels a force. So we know it's going to feel a force, and we know they're going to attract. So it's going to move in this direction, and that's why the arrows point in that direction. So that's just a little convention you should be aware of. But we know this positive charge creates an invisible electric field. And we know nearby, the electric field's really strong. But we know the farther we get, the weaker the electric field. And all the way out here, the electric field will be very weak. So how do we determine the magnitude of the electric field at this particular location? Well, we use this equation. We use this very simple equation. And later on, I'll go into more detail about this equation. But remember, the key point of this video, if we have an electric field and we throw in a charge in that electric field, we'll get a force. We have an electric field, we throw in a charge, it's going to feel a force. How do we determine the magnitude of that force? We simply use this equation. We take the magnitude of the electric field multiplied by the magnitude of the charge that was thrown in that electric field. You just multiply them, and that tells you the force that charge is going to feel because of that electric field. That electric field is going to exert a force on that charge. You can determine the magnitude of that force using this equation. So again, it's a little complex the first time you see it, but with time it should make more sense. So let's go into more detail. So we know this positive charge creates those invisible electric fields. We already explained it. It makes those electric fields in all directions. So let's just focus on this region. So what if you're curious the magnitude of the electric field at this particular location? We know we have an electric field at this particular location. How do we determine the magnitude of the electric field here? Well, again, we use this simple equation. And what if we were interested in the magnitude of the electric field here at this particular location? Well, again, we just simply use this equation. So let's do an example. Let's say, for example, we had this positive 2 coulomb charge. So we know all charges create these invisible electric fields. So let's say we had a positive 2 coulomb charge and we were interested in the strength of the electric field 1 meter away from this positive 2 coulomb charge. How do we determine the magnitude of the electric field at this particular location 1 meter away? Well, again, we simply use this equation. So this K is Coulomb's constant. So this is just a constant you can find in any textbook, and I recommend you just memorize. So this K constant is 9 times 10 to the 9 using SI units. So this I just recommend you memorize. It's Coulomb's constant. This Q represents the magnitude of the charge that's creating the electric field. Because we know it's this charge that's creating the electric field. So if we want to find the magnitude of the electric field at this particular location, we need to know the magnitude of the charge. That charge will have an impact on the strength of the electric field. So this Q represents the magnitude of the charge that's creating the electric field, and this R represents the distance we're interested in. So we know this positive 2 coulomb charge creates an electric field, so we're interested in the strength of the electric field 1 meter away from that positive 2 coulomb charge. So those are the only two values we need. We need the magnitude of the charge, and we need to know the distance that we're interested in. And if we plug in those values, that'll tell us the strength of the electric field at that particular location we're interested in. And remember, this r, this distance, gets squared. It's just the way the formula works. And again, you might say, why is this r? Why isn't this just d for distance? Why is this r? Well, again, you can think of it as a radius. And if you're interested in any particular r, the strength of the electric field there. But again, so remember, the big picture idea is we have this positive 2 coulomb charge, so it creates an electric field. And we're curious specifically 1 meter away the strength of the electric field at this particular location. We can determine the strength of the electric field there using this equation. We just plug in all our values, the magnitude of the charge and the distance that we're interested in, and just multiply these values, cancel out the units, and we will get our answer. So now we know it. 1 meter away from a positive 2 coulomb charge, the electric field will be 18 times 10 to the 9 Newton coulombs electric field strength. So now we know. But what if we were interested in the electric field here? We know this positive 2 coulomb charge creates an electric field. So what if we're interested in the strength of the electric field all the way out here? So let's solve it. Let's say this is 3 meters away. Let's say we're interested in the strength of the electric field 3 meters away. Well, we know how to determine the strength of the electric field. We use this equation. This is Coulomb's constant. This is the magnitude of the charge that's creating the electric field, so positive 2 coulombs. But now we're interested in the strength of the electric field 3 meters away. So we take that 3 meters and plug it in, and remember, it gets squared. That's the way the equation works. So now we plug in these values, just multiply them, and now we'll solve it, we'll get our answer. So now we know if we have a positive 2 coulomb charge, 3 meters away, the strength of the electric field there will be 2 times 10 to the 9 Newton coulombs magnitude of the electric field. So now we know. And again, so the point is, what determines the strength of an electric field at a particular location? Well, the charges that create the electric fields, that's important, and the particular distance those charges are. Those are the two terms that are important. How far we know if this charge, the farther we get, the weaker the electric field. So the distance is important. The distance has an impact on the electric field, but also the magnitude of the charge. That also has an impact on the electric field. For example, let's say under these same conditions, instead of a positive 2 coulomb charge, let's say we had a positive 4 coulombs charge. And we were interested in the strength of the electric field here 1 meter away and the strength of the electric field here 3 meters away. Well, again, we would have stronger electric fields. You can plug in all the values and solve, and we would get stronger electric fields. The strength of the electric field here increased because the magnitude of the charge that created the electric field increased. But again, so the point is, are these charges, they create electric fields, and if you're interested in the strength of the electric field at any particular location, you use this equation. So now we know. Remember, what was the key point of this video? The key point was whenever we have an electric field, if we throw in a charge in that electric field, that charge will feel a force. So we know right here the magnitude of the electric field under these conditions was 18 times 10 to the 9 Newton coulombs. That was the strength of the electric field at this particular location. So what's going to happen if we throw in a 1 coulomb charge in this particular electric field? We know it's going to feel a force. That's what electric fields do. Electric fields exert forces on charged particles. How do we determine the magnitude of the force? We throw in this charged particle. We know it feels a force. How do we determine the magnitude of the force that this charge feels? We simply just multiply them. It's that easy. We know the strength of the electric field. We know the magnitude of the charge. We just multiply them. Coulombs cancel, and now we know. If we have this electric field strength, and we throw in a positive 1 coulomb charge, that positive 1 coulomb charge will feel 18 times 10 to the 9 newtons of force. So now we know if we throw in this charged particle, we know it's going to feel 18 times 10 to the 9 newton force in this particular direction. Why is it in this direction? Because again, remember, the electric field points in the direction that a positive charge will move. So now what if we threw in this positive 1 coulomb charge in this particular electric field? Well, we know whenever we have an electric field and we throw in a charge, we know that charge will feel a force. How do we determine the magnitude of the force that this charge will feel due to this electric field at this particular electric field strength? Well, again, we just multiply them. Coulombs cancel. Now we know. If we throw in a positive 1 coulomb charge in an electric field of this particular magnitude, it'll feel this particular force. And again, the coulombs just cancel, and now we know. So again, these are the units of electric field. It's newtons per coulomb. So now if you throw in a coulombs, the coulombs cancel, and now you get a force. Now you determine the magnitude of the force. So what if we threw in a negative 3 coulomb charge particle in this particular electric field? But remember, whenever we have an electric field, if we throw in any charged particle, the electric field will exert a force on that charged particle. So now we know we have this electric field strength. So now we throw in a negative 3 coulomb charge. Well, again, we just multiply them. Coulombs cancel. Now we know that 3 coulomb charge, negative charge particle is going to feel force. How strong of a force? Negative 54 times 10 to the 9 newtons of force. And again, we know that force is going to apply in this direction, because remember, the convention is the electric field points in the direction a positively charged particle will feel. But this is a negatively charged particle, so we know it'll feel that force in the opposite direction. And again, what if we have an electric field strength of 2 times 10 to the 9 Newton coulombs, and we throw in a negative 3 coulomb charge in that electric field strength? We know it'll feel this force, this magnitude of that force. So we throw in this negatively charged particle, it's an electric field, so we know it's going to feel force. And again, it's going to point in the opposite direction of the electric field, because again, electric fields by convention, humankind has decided that to draw electric fields pointing in the direction that a positively charged particle will go. So because it's a negatively charged particle, we know it'll feel this force in the opposite direction.